Suppose you have the following circuit in which the switch closes at time equals 0, and you are asked to determine the voltage across the capacitor as a function of time after time equals 0. Note that when this switch closes, this short will cause this section of the circuit to be isolated from this section of the circuit, leaving this section of the circuit a parallel RLC circuit. So step 1 is to determine the form of the equation for the parallel RLC circuit, which we will now redraw. I have not even bothered to draw the inductor and capacitor in this case. If alpha equals 1 over 2RC and omega naught equals 1 over the square root of LC, then alpha equals 500 and omega naught equals 354. Alpha is greater than omega naught, so we have the form V of t is equal to a1 e to the s1t plus a2 equal to the s2t. And s1 and s2 can be found by this equation to be s1 equals negative a54 and s2 equals negative 146. Thus, V of t equals a1 e to the negative a54t plus a2 e to the negative 146t. Now we need to determine the initial conditions, the current in the inductor and the voltage across the capacitor. Note that we want this voltage across the capacitor, which means the current in the inductor needs to be in the downward direction. However, in the original circuit, that would represent a current going to the left. I hope you can see why that is so. So we need to determine this current, IL, because that would correspond to I naught in the switched circuit. And of course, VC. Let's redraw the circuit before time equals 0. The inductor acts as a short, and then we have a 50 ohm resistor, and then the capacitor is simply an open. So this 50 ohm resistor actually has the voltage of the capacitor. The voltage of the capacitor can be easily determined using the voltage divider. 40 times 50 over 80 gives you 25 volts is equal to VC. But what about the current? The current in the circuit I is simply equal to 40 over the sum of the resistors. 80 is equal to 0.5 amps. In order to get the current in the inductor for our convention, we simply need to apply a negative sign. So I naught is equal to negative 0.5 amps. So we have also V naught equals 25 volts. Finally, we can use this equation for dV dt at time equals 0 to determine that dV dt at time equals 0 is exactly 0. Wow, amazing! Now we can plug in the conditions V naught equals 25 and V naught prime equals 0 into this equation. At time equals 0, 25 equals a1 plus a2, because e to the 0 is 1. Now V prime of t is negative a54 a1 e to the negative a54t minus 146 a2 e to the negative 146t. And at time equals 0, 0 equals negative a54 a1 minus 146 a2, and solving this system of equations gives us a1 equals negative 5.156, a2 equals 30.16, and therefore V of t is equal to, we can verify this makes sense by plugging in t equals 0 and noting that 30.16 minus 5.156 is roughly 25. Which is the voltage of the capacitor that we expected. So we have successfully solved this problem. If you wanted to determine other pieces of information in the circuit, like the current across the inductor, we would need to use rules like Kirchhoff's voltage law and Kirchhoff's current law. So for our final step, why don't we determine an expression for the current through the inductor at any given moment? If we select the following node and note IL, IR, and IC as follows, we can write that IL plus IR plus IC equals 0. It is evident from Ohm's law that the current across the resistor is VC over 50 ohms, and from the rules of capacitors that the current across the capacitor is 20 microfarads times dVc dt, and if we subtract IL to the other side, this is equal to negative IL. All we'd have to do to get an expression for the current across the inductor is plug in our expression for the voltage and our expression for the derivative of the voltage, and then wiggle around with math and annoying numbers until we finally get an expression for the current. As you can probably tell, I'm uninterested in doing all of that mathematical numerical wiggling, but what you've seen me do here is use KCL to get an expression for the current of the inductor in terms of values we already know, values we already have expressions for or can get expressions for in the case of the derivative of the voltage across the capacitor.